Hi students. Now we are going to derive the relation between angular momentum and angular velocity. Okay. First of all, we must remember what is the relationship between linear momentum and linear velocity. Okay. So linear momentum, we have studied that P is equal to mass into linear velocity. Like that, angular momentum must be L. Okay, and the mass, the role of mass played in the rotational motion is what? Moment of inertia. And we have to substitute V by angular velocity omega. Just analogous terms. So the first equation is true for translatory motion. The second equation is true for rotational motion. So what we are going to derive is angular momentum and angular velocity. That is L and omega relationship. That is what we want to derive this equation. L is equal to I omega. So first itself I have told you which equation or which relationship we are going to derive. Okay? Fine. Now let us look at the picture. This red boundary line shows a rigid body which is assumed to be made up of so many number of point masses. One such point mass M I have chosen, which is inside the rigid body. On that point mass, some force is acting. So the particle point mass is revolving in a circular path. So these are the trajectories. Okay, trajectories are locus of all the points along the path of the particle. So when the entire rigid body is rotating, each particle will be revolving in a circular path. Okay, what will be its linear velocity is V. Okay, its linear velocity is V, which is tangential to the circular path. Along the same direction, who also is acting is the linear momentum P. And the angular momentum L vector is perpendicular to R vector and P vector. Is it not? So L is upwards. So what is the usual expression? Usual expression for this angular momentum, we start with the definition of angular momentum L. So angular momentum is given by L vector is equal to R vector cross product linear momentum vector. So when I write R cross P, what you must keep in your mind is a moment of the linear momentum. Understand? So this is R cross P and its magnitude is L is equal to R into P into sine theta. In this picture I have taken the angle theta is equal to 90 degree, maximum value of the momentum. So this is sine 90. L is equal to R into P. So this is the first step. Understand? Have you understood? So what is the magnitude of the angular momentum? L is equal to the product of the radius vector or position vector and the magnitude of the linear momentum. Okay, what is the linear momentum? P is equal to mass of the point particle into its magnitude of its linear velocity, mv. Is it not? So this is the second equation. I am going to substitute for P equal to mv in equation 1. Therefore, what is L now equal to Rmv. Rmv. Okay. Now I have told you the body, entire rigid body is exhibiting rotational motion. But what about each and every point particles or point masses present inside the body? They are exhibiting circular motion. So they possess two velocities, is it not? One is linear velocity V, the other one is angular velocity omega. So omega is the angular velocity. Angular velocity. Okay. Where V is what? The linear velocity. So we have already derived in the chapter kinematics. There is a relationship between V and omega, and in magnitude it is V is equal to what? R omega. The velocity, linear velocity is equal to R times radius times the angular velocity. Is it not? Now look at this equation. Here there is a term V. I am going to substitute V is equal to what? R omega. Therefore, L becomes equal to R into M into R omega. So this is R into M into R omega. So R into R can be taken as R square. Okay. So R capital L is equal to bracket M R square into omega. Already we have studied the product of the mass of one particle into square of its distance from the axis is the opposition offered by the particle to the rotational motion of the body. That is called as what? Moment of inertia of one particle. Is it not about the axis? Okay. So this mr square is called as what? Moment of inertia of a single particle. Moment of inertia of a particle or point mass about the axis of rotation. Therefore, for the rigid body, for the entire rigid body, what I can say now, this L must be equal to sigma mr square. For the first particle I is equal to 1, nth particle I is equal to n. So I can also rewrite this as what? Sigma miri square into omega. Here one very interesting fact you should understand. The linear speed or the linear velocity, magnitude of the linear velocity v will be different for different particles. But the angular velocity omega is always constant. Is it not? All particles, they describe different circles of different circumferences in the same time. So their linear speeds will be different. But do all the particles at different radii subtend the same angle 360 at the center or not for one revolution? So omega is a constant. It is not different for different particles. Understand? So the masses of particles are different. Their distances from the axis are different, but angular velocity is the same. So sigma miri square. So what is this sigma miri square? Sigma miri square. This is the algebraic sum of the mass of the particles and the square of the distances from the axis of rotation. Is it not? So this is equal to the moment of inertia, that is I. I is a scalar, which is a constant provided the axis is fixed. So I can write what? L is equal to, therefore L is equal to I omega. So this is in scalar form. So angular momentum is equal to moment of inertia times the angular velocity. Understand that? So in vector form, if you write, L is a vector. Okay, angular momentum is a vector, but moment of inertia is a scalar, and angular velocity is already a vector, which is also acting perpendicular to the plane containing r vector and p vector, r vector and v vector. So L vector and omega vector are upwards for anti-clockwise rotation and downwards for clockwise rotation. Understand? So this is in vector form. So we have derived the relationship between angular momentum L and angular velocity omega. So this equation is analogous to linear momentum vector is equal to mass into linear velocity. Understand? Every time whenever we derived the relationship in the earlier derivations, we have compared with linear motion. So this equation L is equal to I omega is true for rotational motion or angular motion, whereas it is analogous to this equation P vector is equal to M into V vector in translatory motion or linear motion. I hope you must have understood well. Fine.